Hi, everyone, and welcome to the AP Statistics live learning session for bivariate data analysis. Today, I'm going to be going over an overview of your model on bivariate data. Most of it's going to be just explaining what you're going to see in this unit and what that means for a set of data. So follow along with me. So two questions of bivariate data analysis is, which it's not showing, there it is. What is the degree of linearity? Which pretty much just means, are we able to determine that there is a linear association in the variables of a set of data? So again, can we say do a scatter plot and draw a line through it reasonably? And then the second question is, what is the degree of association? So how strong is that line? Is it pretty well going through all the points? Or maybe all the points are just all over the graph randomly. And in that case, the line would not be a good degree of association. So there is going to be an explanatory variable, which is also known as the independent variable. This is known as the x value, or the variable on the horizontal axis or the x-axis, if you took algebra, which I'm sure you did. It's usually what the researcher is trying to manipulate. So you'll manipulate the x variable and see how the y variable reacts. The y variable is the response variable. Again, it's how it responds to the x variable. So it's the dependent variable, or the y, and it's what the researcher is trying to see an effect on. If we want to predict y, what could x be? So these are just some examples of some things that we could predict, possibly based on an independent variable. You could maybe predict the weight of human males. Yeah, what could x be? Well, x could be their height, right? Maybe we would look at a man's height to predict their weight. So that would be an answer to number one. Number two, how could we predict a math SAT score? Think in your mind, how could we predict a math SAT score? What quantitative variable? Well, what about the GPA of all math courses the student took in high school? That would probably be a pretty good predictor of the math SAT score, right? What about number three, predict college freshman GPA? Well, if we wanted to predict that, we could probably use the high school GPA, right? Think about number 4, 5, and 6. Think about those on your own. Pause this video and ask yourself, if we want to predict blah, 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 whatever it says there, what could we use to predict that? A scatter plot, as you're well aware of by now, is a graph of two variables with a dot to represent each observation. So all of those dots on that scatter plot represent the income, and then the number occupied for that particular income. And those are actual values that were collected from a sample. When you're looking at a scatter plot, you want to look at the shape. Does it look linear? That's almost one of the first things you're going to look at is, does it look linear? Are there any unusual points or outliers? Although you have to actually, calculate to do calculations to determine if there's an outlier, you can still look at the graph and maybe predict what might be an outlier. Direction is the linear relationship, positive or negative. And then the strength, is the line strong, meaning does it go through most of the points pretty well, or are the points very far away from the line? Correlation. This measures the strength of the linear relationship between the variables. This goes along with that last one in the list here on strength. So to measure the strength, you could actually find the correlation coefficient. R is the symbol for correlation, and it takes on values between -1 and 1. 0 means no linear relationship. That would mean if you just had a scatter plot and the points were just all over the place, and there really was, you could still create a linear regression equation, or draw a line somewhere that sort of looks like it might go through. But if the correlation coefficient is 0, then there's no linear relationship. And we'll talk about how to calculate the correlation coefficient in a future recording. It's also in your course, of course. So, and then anything between negative and 1, or if it's exactly -1 and 1, that means a perfect linear relationship. And the closer you are to -1, or the closer you are to 1, means that the stronger the linear relationship is between the variables. So let's not confuse correlation with causation. Just because you have a high R value does not mean that X causes Y. So be careful. There could be a lurking variable that is actually the cause. So correlation just shows that the variables correlate, like one may predict the other, but it doesn't necessarily mean that it causes the other. We can just use it as a prediction. So minutes late to work. The direct cause could be late to work and rain. So rain, the amount of rain that, say, let's just say this, say the number of inches of rain on the morning commute, it directly affects the number of minutes a person is late to work. Or the reverse cause and effect, late to work and poor relationship with the boss. So that could also be a reverse cause and effect. A third variable might be something such as the person has a certain number of children at home. That could affect how late a person is to work, but it may not be on the graph or on the comparison of the variables. And then there might be a coincidence. I really doubt that a person's height is going to predict how late they are to work, but we could certainly plot that on a scatter plot. It would probably be very, very scattered and have a correlation coefficient close to 0, but it is something that we can compare. A regression line. So you may have heard me just a few minutes ago mention a linear regression equation. This is your regression line. It's a linear model created by bivariate data set. So bivariate data, again, is where you have two variables and you're comparing the relationship between them. The equation of that line represents the line of best fit and serves as the prediction line. So the prediction line can be used when you don't actually have an X value and a Y value for a certain quantity that you want to predict. We'll talk about how to calculate that regression line too in a little later on in the session. So regression line formula, well, as you know from algebra, the equation of a line is y equals mx plus b. Oops, sorry, I'm trying to get my annotations out. There we go. In algebra, it's y equals mx plus b. In statistics, it's y equals a plus bx. So really, we're just swapping these and doing b is in the place of m and a is in the place of b. So don't let that get confusing. But this isn't algebra. This is statistics. So you might want to just write that down. That the standard form of the regression line is y equals a plus xb. A equals the y-intercept, and the value of y if x equals 0 often has no real meaning in the context. For example, if you were using, I don't know, what was one of those examples that we had before? Oh, a person's weight and height. Okay, so is it possible for a person to weigh 0? Well, if weight and height are related, no, there's not possible for a person's weight to be 0 or their height to be 0. So even though we do include the y-intercept in the equation, it often is not really, it doesn't really make sense in the data. But we do need it in the linear regression equation because that's going to, well, indicate where we put the line on the graph, how far up or how far down, where exactly it needs to be. The slope is good, of course, but we also need to know exactly where the line needs to be on the graph. So the slope, again, from back going to algebra, is for every increase of 1 unit in the a, which is the explanatory variable. The y, the response variable, increases or decreases by this amount. So it's delta y over delta x, or you can say y2 minus y1 over x2 minus x1, or you can say rise over run. Those are all of the ways that we did it in algebra, and you're actually going to do it the same way in statistics when you find the slope. So let's interpret the slopes of regression lines. We could have something like the length is equal to 90 minus 3.2. That would be temperature in Fahrenheit. If this is the case, or times the temperature, so that's what it would be. Let's take a look at this first one. We would have, hold on one second. Explanatory, again, is the x. Response variable is the y. Might want to write that down as we're going through these examples. X is the explanatory, y is the response. So in this one, the 3.2, well, actually it's a negative 3.2. This is going to be the slope, and then the y-intercept is 90. So let me write this out at least just for this first one. B and A, and really I should be doing A then B, right? I mean, like I said, this isn't algebra, this is statistics. So let's keep this in order. A plus B x. So the y value represents the length. That could be in inches, centimeters, whatever. The x value represents a temperature in Fahrenheit. A, which is your y-intercept, is positive 90. And B, which is your slope, is negative 3.2. Remember that if you have a minus 3.2, that's going to be that your slope is negative. But if, for example, in this next one, if you have a positive, that means your linear regression line has a positive. So you can take a look at the following examples on income and score. and pause this video and see if you can write those down, and then we'll go over just the first one. All right, so in this next one, and I'll just use a different color. No, it won't. Takes too long to get those colors out. Y equals A plus BX. So Y is the income, probably in dollars. A is the y-intercept, which is 22.3. B is 0.65. That's the slope. And then X is the years of service. And that would be our explanatory variable, just as the income would be the response variable. And that makes sense because usually the longer you work at a company, the higher your income. And that's really what this is saying here, is that with a positive slope times the years of service, you're going to increase the income to make the prediction. The goal of that regression equation is to be able to predict a response based on a value of an explanatory variable. Let's go back to the previous example. Income, years of service. Let's say that you're at a particular company and you want to know how much you're going to make when you've been at the company for 5 years. Because maybe you're like, I don't know if this job has any potential. I don't know if I want to stay here. If I have a lot of potential to make good money, maybe I'll stay here. But if in 5 years I'm still not making much money, probably going to consider some other options for a career. Well, you could take 5, which is your years of income, multiply it by 0.65, and then add 22.3, and that would be a prediction of what you might make at that company in 5 years. Now, it doesn't mean it's for sure, but it is a good prediction if that correlation coefficient is a pretty high number. And some other examples are you can use it to predict a college GPA based on an SAT score. You can also use it to predict how much a baby's temperature will go down with X amount of Tylenol. So again, our goal of the regression equation is to predict a response. Now the residual. All right, so the residual is the difference between an actual value that was used to create the regression equation and then the predicted value using the regression equation. If you look on Khan Academy, there's really a good video there that has a graph and everything and explains how to find the residual with the graph. Here's the formal definition. The amount in the y direction that a point is from the regression line. So the residual is the actual value minus the predicted value. That's always the case. It's always the actual value minus predicted value. If you have a positive residual, that means the point's above the line, and the negative residual, the point is below the line. Let me see if I can find that video for you too. Hold on a moment. All right, it's probably going to take me a little longer than I thought, and you probably don't want to sit here and wait for me. But if you go to Khan Academy and just click on the AP Statistics course, you'll be able to click on the module on bivariate data, and you can look for the video there on residual. It's really good because it gives you a good visual of this part right here, talking about the positive and negative residuals and how one would be a point above the line, and the negative would be that the point was below the line. But again, the residual is a comparison of your values that you actually used to do your scatter plot, and then the value that is created by using the linear regression. If you haven't viewed all of the content on this what I'm going over right now, don't worry, you'll understand it when you take a look at it. It's kind of hard to understand if you didn't read the module first. The line of least squares is also the regression line. It's the same thing. And the best fit minimizes the squares of the residuals of each point from the regression line. Khan Academies also does a good job of showing that. But basically what you need to know is that the regression line and the line of least squares, it's the same thing. It's just another word for it. So here's an example on age and blood pressure. We can probably imagine that the older a person comes, probably the higher their blood pressure, right? Young people are very healthy. And as people get older, their blood pressure tends to increase just due to getting older. So here's some data here. With some corresponding age and blood pressure and what those might be. And you can see that, let's see, 48, yeah, it pretty well. I don't know how good this correlation coefficient is going to be on here. I think maybe for the most part, we can see that the age has a correlation positively with the blood pressure, but we can use the correlation efficient to say for sure how close it is. So again, as we talked about earlier in the presentation, it measures the strength of the linear relationship, can be positive or negative, and always is a number between 1 and -1. Now, R squared is the coefficient of determination. It measures what percentage of the variation is Y in Y as it is explained by or determined by the variation in X, and it will be given as a percent. This will be on one of either your quiz or your test for this module. I remember seeing it. And 1 minus R squared is the coefficient of non-determination. Well, we all know that percentages add up to 100, right? So this 1 is pretty much like taking 100% minus the R squared, which was the coefficient of non-determination. So flip that around, and when you add up the coefficient of non-determination and the coefficient of determination, you're going to end up with 100%, or you're going to end up with 1, which, let me write this up here, 1.00 equals 100%. And you might have that the coefficient of non-determination is maybe like 0.25. If that's the coefficient of non-determination, then the coefficient of determination, which is represented by R squared, would be 0.75 or 75%. So again, these are always going to add up to 1 or 100%. Same thing if you move the decimal over to the right 2 spaces. The percent of variation in Y is not explained by the variation in X. Okay, so this measures what the variation in Y, which is explained by chance or other factors. So keep that in mind. That's specifically what the quiz or test is asking. And if you need to pause this recording and read that again, please do so. So is the linear model appropriate? So how do we answer this question? We're going to check the scatter plot and the R value for whether it has a strong linearity. And we should also look at the residual plot, which I didn't actually do for you yet. I just mentioned that there was a really good Khan video on this. So let's keep looking. Again, the residual plot is a graph of the residual values compared to the X values. We don't want to see any pattern of residuals increasing or decreasing or fitting any noticeable curves. It'll take you a while to understand why this is true, but let's take a look at some graphs here. This is the residual. What this means is, again, we took the value from the scatter plot and we compared it to the value that you would get if you plugged in that X value into that A plus bx. If you haven't made it to that point in the content yet, go back and read that, and I promise this will make a lot more sense. But this is going to be a good residual. The reason why is we're seeing that it's all spread out. It's wide open. There's not any particular trend here. It doesn't look like it's a line. It doesn't look like it's a curve. It doesn't look like it's an exponential. It doesn't look like anything. It's just all over the place. So this means that the residual is random, and this is a good residual. It means it's probably going to fit the linear regression equation well, as opposed to another type of regression equation. A bad residual would mean that it has a pattern here. This pattern, although it is kind of hard to see, we can see that it sort of, oh, actually, let me draw it. That would be even better. We can see it sort of does like this, like a horn, right? This is a pretty firm pattern once I draw it, right? I mean, it was kind of hard to see at first, but once I draw this pattern, we can see that there is a pattern. If there is a pattern, that means it's a bad residual for the linear regression line. Because what we want, again, is when we want things to be kind of above and below that linear regression line equally. This one is actually showing that as the estimate gets higher, then we're seeing the numbers get further away from the actual values, okay? Here's another bad residual. This is a very, very clear pattern. It looks like a parabola. This would indicate that a linear regression is probably not a good regression for this set of data. And then we always have to consider some unusual points, which of course are the outliers. A point that strongly affects the regression line is usually an outlier, not always. It could be just an influential point that is kind of way off from the other points, but maybe not technically considered an outlier mathematically. So how to check, you'll remove it from the data and recompute the regression line to see if the line changes dramatically. You're probably wondering, you still haven't told us how to compute a regression line. Well, you may have seen it already in the content, but I'm going to show a video here in a few minutes, and then it'll show you how to do that. And usually you'll have to plug in a point to each regression equation to see if it matters, like see how much difference it has made. So again, if you want to know if there is an influential point, take that point and remove it and recalculate the regression line and see if that line changes dramatically. You can graph it, you can graph the line. It may be steeper, it may be flatter, it may be further up, it may be further down on the graph. And an outlier, it's a point in the regression analysis, can be an outlier. You can have an outlier that it's an outlier because of the X value or because of the Y value or both. And how to check, examine the graph to see if one point seems far away from the rest of your X or Y direction, and then do an outlier test. So there's a formula for that, as you know from the last module. Extrapolation. This is the goal of the regression is to create a model to predict, but you must be careful how far beyond the range of the original data that you predict for. This again goes back to that example where I was talking about using a person's height to predict their weight. At some point, this isn't going to work because there's only a reasonable weight and a reasonable height for adults in this world. So if you go really low on the range of height, it may not really, this linear regression model might not really work that well. Or if you're really high, like say that you had an adult that was 7'2", because that's so much taller than anything in your range of the original data, we might have to be careful about whether or not that's really going to be a good predictor. So predicting Y for an X far beyond the range is called extrapolation. And if a linear regression model is good, meaning it has a strong R, it's linear, and the random residuals, are all scattered, that still doesn't mean that X causes Y. So just keep that in mind. I know we already talked about that, but that's worth mentioning again. And so for a researcher to assert that X causes Y, the data must have come from a planned controlled experiment, not just the data. You actually have to have an experiment where you have a control variable, and you're manipulating, one group of, I guess, people or whatever else bacteria, things like that. And you actually do an experiment. That's the only thing that is going to determine causation. Here's an example. One thing we talked about: if we have a regret or a correlation coefficient R that equals negative 0.62, what can we say about the level of association between X and Y? Well, first of all, we can say that that's negative. So that means on the graph, we are going to have a negative association. So it's going to slope downwards. And also, it's going to be moderate because the slope is 0.6. So that would be something estimated to negative 6/10. Or if we really just want to rough, make it really rough, that's really about negative 1/2. So on our graph, we would go down 1/2, down 1/2, down 1/2, and so forth. Let me erase that and actually do a line to represent that. It would be something like this: a moderate negative linear association. And because remember that we talked about the variation, only 38% of the variation in Y is explained by the variation in X. You would get that by taking 1 minus 0.62. That gives you 38. And so that would tell you that only 38% of the variation in Y is explained by the variation in X. And re-expressing data is transforming it if the linear model is not appropriate. So for example, let's say that you look at the data and it doesn't really look like a line. It looks more like a curve. Maybe it could be anything. I mean, it could be exponential, trigonometric, whatever. But we're going to focus primarily on exponential in this course. So if we want to transform the data, and the reason why you would want to do that is because we have so many, I guess, different tools that we can use to evaluate a linear model. You may want to take something that's exponential or something, or another model, and convert it to the linear model so that we can use all of those tools that we have in our hands. So that is when you re-express the numbers using some algebraic operations that take the curve out of the original data. Some examples would be like to take the square root, to take the log or natural log, or to use reciprocals. And I'm actually thinking of another video in Khan Academy that shows a function. Well, I shouldn't say function. It shows a scatter plot where there's data that looks like an exponential growth. And he took the log of all the Y values, and all of a sudden he had a new X and Y coordinates, and it looked just like a line. And so we can always work backwards to find out what the values are before taking the log. But if we can somehow transform the data by doing something to all the X values or all the Y values, mostly it would be where we do something to all the Y values and make it look like a line, then we can use all of those tools that we use for a regular lineal model that was a good fit. That concludes everything for today, except for the video I'm about to show you on how to write your linear regression equation. So I'm going to play that for you.
In this video, we're going to focus on linear regression using the least squares method. And this approach will help us to write a linear equation that best fits the data in the table shown below. So let me give you a visual illustration. So let's say we have these data points, which I'm going to highlight in blue. Now, these data points don't all fall on a straight line. However, what we can do is we can calculate the equation of a line that best fits this data, where all of the points are as close to as possible to that line. Now, what we're going to do is we're going to use a method called the least squares method to find the equation of the line. And then once we have it, we're going to test that equation to see how accurate it is in giving us the y values when we input the x values. And then we're going to confirm our answer using Excel. So let's begin. So the first thing we're going to do is we're going to create a table. This table is going to have 4 columns. So the first column is going to be x, the second column is going to be y, the third column will be the product of x and y, and then the last column will be x squared. Now let's plug in the values. So the first x value is 1, next is 2, and then 3, 4, after that is 5, 6, and 7. Now let's write the corresponding y values. So it's going to be 1.5, 3.8, based on what we see in this table, and then it's 6.7, 9.0, 11.2, 13.6, and then 16. Now for the next column, we need to multiply x and y together. So 1 times 1.5 is 1.5. 2 times 3.8, that's going to be 7.6. 3 times 6.7, that's 20.1. 4 times 9 is 36. 5 times 11.2, 56, and then 6 times 13.6, that's 81.6. Now 7 times 16. 7 times 10 is 70. 7 times 6 is 42. 70 plus 42 is 112. Now let's calculate x squared. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. Now the next thing we need to do is we need to take the sum of each column of numbers. So let's go ahead and do that. So let's start with the sum of the x values. So let's add up every number in the first column. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7. That's going to be 28. Now let's take the sum of the y values. So 1.5 plus 3.8 plus 6.7 plus 9 plus 11.2 plus 13.6 plus 16. So that's 61.8. Now, let's find the sum of the next column, the sum of the xy values. So 1.5 plus 7.6 and so forth, all the way to 112. If we add those 7 numbers, we're going to get 314.8. Now let's find the sum of the x squared values. So 1 plus 4 plus 9 plus 16 plus 25 plus 36 plus 49. That's going to be 140. Now let's write down the important information that we've gleaned from this table. The sum of the x values is this number here. So that's 28. Now the sum of the y values is 61.8. These values are important because it's going to help us to calculate the slope and the y-intercept of the linear equation. Next, we have the sum of the xy values, and that's 314.8. And finally, we have the sum of the x squared values, which is 140. So now that we wrote that, let's get rid of this. So the linear equation will be in this format. Y is equal to mx plus b. In statistics, you might see an equation like this. Y is equal to b0 plus b1x. So what you need to know is that the slope, the number in front of x, is m or b1. They're the same. So I'm just going to write that here. So the slope of the line is equal to m, which is how you'll see it in algebra, but in statistics, you might see b1. Now the y-intercept in algebra is represented by the symbol b. So I'm going to highlight that in blue. In statistics, you'll see it as b0. So these two numbers, they're the same. In this video, I'm going to focus on the linear equation in slope-intercept form as taught in algebra. That is in this format, y is equal to mx plus b. But I want you to see the relationship between how a linear equation is described in algebra compared to how it's described in statistics. Now, let's talk about how we can calculate the slope in this example. So the slope is equal to n times the sum of the xy values minus the sum of the x values times the sum of the y values. And then we're going to divide that by n times the sum of x squared minus the sum of x squared. By the way, n is the number of values that we have in our data. So we have 7 points, thus n is 7. So let's plug everything into the slope formula. So this is going to be 7 times the sum of xy, which is 314.8, minus the sum of x. So that's 28 times the sum of y, which is 61.8, and then divided by n. Now the sum of x squared, that's 140, and then minus the sum of x, which is 28, but we're going to square that. And so this is what we're going to get. So now let's plug everything in. 7 times 314.8 minus 28 times 61.8, that's 473.2. And then 7 times 140 minus 28 squared, that's 196. So dividing these two numbers, this is going to be 2.4142857. So I'm just going to rewrite that at the bottom so we can save that for later. So this is the slope of the line. I'm not going to round it early because we're going to need our m value to calculate our b value. So now we can get rid of this. Now let's calculate the y-intercept, b. So this is going to be the sum of the y values minus m times the sum of the x values divided by n. So the sum of the y values, that's 61.8. Our m value, we're going to use the most accurate number that we have to get an accurate b value. So this is 2.4142857. If we round it too early, it will affect our b value. So that's why I don't want to round it too early. The sum of the x values is 28 divided by n, which is 7. So if you plug this in, you should get approximately negative 5.8 on the numerator divided by 7. This will give you a b value of negative 0.828571. Alright, so now let's get rid of this, and we no longer need this information. So to write the linear equation, we need to plug in our m value and our b value into the slope-intercept equation. So it's going to be y is equal to, I'm going to round the slope to 2.41. And then I'm going to round b to negative 0.83. We don't need to use the exact answer. So this will be a good enough approximation of the data that we have in the table. And let's check it. So let's see what our y value will be if we plug in an x value of 2. So this is going to be 2.41 times 2 minus 0.83. And so we get 3.99. Now 3.99 is not too far away from 3.8. So that's a good approximation. Now let's try plugging in a different value. Let's go with 5. So 2.41 times 5 minus 0.83. So this is equal to 11.22. 11.22 is very close to 11.2, so that's an even better approximation. Now let's try one more. Let's try an x value of 7. In this case, I get 16.04. 16.04 is very close to 16. So thus we could see that this linear equation fits the observed data very well. So now you know how to use the least squares method when performing linear regression. That is, when you need to write a linear equation that best fits the observed data of some type of experiment or something. Now what we're going to do at this point is that we're going to use Excel to quickly get the slope and the y-intercept, because once we have m and b, all we need to do is plug it into this equation and we have our linear equation that best fits the data. And sometimes when you're performing a science experiment, or if you have a lab report and you need to write a linear equation that best describes the data, Excel is a quick and simple way to do it. It'll save you a lot of time. So here we have Excel, and what we're going to do is we're going to plug in our x and our y values into columns B and C. So let's start with the x values. So 1 is 7, and then let's input the corresponding y values. So it's 1.5, 3.8, 6.7, 9, 11.2, 13.6, and 16. Now the next thing we need to calculate is the slope. So in cell C9, type in equal slope, open parentheses. Now notice that it says the known y values. You want to highlight the values in the y column. Once you do that, press comma, and then it says the known x values. Highlight the values in the x column, close parentheses, and then hit enter. And notice that we get the same slope, 2.414, 2857, which is what we got earlier in this video. So now we're going to calculate the y-intercept using Excel. So if you type in equal, intercept, open parentheses, highlight the y values, press comma, and then highlight the x values, close parentheses, press enter. Now it gives you the b value, the y-intercept, which is negative 0.828571, which is what we had earlier as well. So as you can see, this is a very time-saving method to calculate the slope and the y-intercept of the linear equation that best fits the data. So that's it for this video. Hopefully you found it to be educational. If you like it, don't forget to hit that subscribe button, and thanks for watching.
All right, so hopefully you were able to view that video. Sometimes this meeting platform is not all that has some errors and stuff. But if you could not see it or could not hear it, you can go to the chat box and either copy and paste or write down and then type into your web browser that video. It's by the chemistry tutor. He does a really good job, I think, of explaining things. And then you can also, as an additional resource, go to Khan Academy and go to the AP Statistics course and go to Bivariate Data. And if you do a word search on that web page for residual, you'll find the other video I was talking about. And it will tell you how to graph the residual points. So if you have any questions about this or anything else in the class, I'm here to help. Thanks for listening. Everyone have a great day.